And welcome to the third part of our presentation on fundamentals of microwave communication and waveguides. Myself Sanjit Kumar Singh, lecturer in Electronics and Telecommunication Department at Praveen Patil College of Diploma Engineering and Technology. After going through this presentation, the learner will be able to explain the properties of the given parameters for the circular waveguide with example, describe with relevant sketch the field patterns of the given mode of a rectangular waveguide, compare the features of circular and rectangular waveguide for the given parameters. The topics that are covered are rectangular waveguide modes, the different modes TE, TM, transverse electromagnetic mode, TEM, their field patterns, then circular waveguide, advantage, disadvantage and applications of circular waveguide, and of course the comparison of the circular and rectangular waveguide. Moving on. So what do you mean by mode? By mode, we mean the propagation mode, the path a microwave signal will follow inside a waveguide. So there are different paths possible, but either the magnetic field or the electric field must remain perpendicular to the direction of propagation of the wave. There are a number of possible modes for the given size of the waveguide, which increases with the frequency. It is the dominant mode in the waveguide that is normally used. The different types of waveguide modes often indicates the transverse electric and transverse magnetic modes with the integers after them, T, E, M, N. The M and N are always integers that can take on separate values from 0 or 1 to infinity. So this indicates the wave modes within the waveguide. Only a limited number of different M and N modes can be propagated along a waveguide dependent upon the waveguide dimensions and formats. For each waveguide mode, there is a definite lower frequency limit which is called cutoff frequency. Below this frequency, no signal can propagate along the waveguide. As a result, the waveguide can be seen as high pass filter. So what are the types of modes? First, TE, that is transverse electric mode, or is also known as H mode, magnetic mode by Europeans. This is the mode in which there is no electric field in the direction of propagation, but the electric field vectors always remain perpendicular to the direction of propagation. The second one, transverse magnetic mode, which is also called E mode by Europeans. In this mode, there is no magnetic field in the direction of propagation, but is perpendicular to the direction of propagation. The third one, transverse electromagnetic mode, TEM mode. In this mode, neither electric nor magnetic field is present in direction of propagation. So a rectangular waveguide is not supporting the TEM mode, only TE and TM mode is supported. So in the adjacent figure, right hand side, we can see the different field patterns and the propagating modes, transverse, TM, TE and TEM mode. Next, the TE mode or H mode. This mode is characterized by Ez is equal to 0, Hz is not equal to 0. That means no electric lines of field along Z direction. Z is the direction of propagation, but magnetic field exists along Z direction which convey the information. So there are different modes, TE01, TE10, TE11, TE20 and so on. Out of these, TE10 is the dominant mode because this is the lowest possible frequency for the rectangular waveguide. Rule of thumb for rectangular waveguides, the TE10 mode of propagation is the lowest mode that is supported, and it is the width A of the cross section which determines the lower cutoff frequency FCO and is equal to half the wavelength of the lower cutoff frequency. And third, the TE20 occurs when the width A dimension equal to 1 wavelength of the lower cutoff frequency. So on the right hand side we can see the electric field intensity is maximum in the center and goes on decreasing towards the side walls along the width, and down we see the different T10, T20 and T30 mode of propagation for the rectangular waveguide. Next we have the TM mode, or also called the E mode, electric mode by Europeans. So this mode is characterized by Hz is equal to 0 and Ez is not equal to 0. That means here M and N value cannot be 0. So at walls the tangential component of electric field is 0 and of magnetic field is maximum. TM11 is the dominant mode of rectangular waveguide in TM mode, but it is lesser than the TE10 mode. For TM mode of the rectangular waveguide, TM11 has the lowest frequency, but compared with that of the TE10 mode, it is still bigger, the frequency is bigger. So TE10 mode is the dominant, overall dominant mode for the rectangular waveguide. So TM0 mode cannot exist in rectangular waveguide. On the right hand side we can see TM11 mode, the field pattern. Question is, why TEM, transverse electromagnetic mode, cannot exist in rectangular waveguide? Think for a while. The reason is there are boundary wall conditions for ideal rectangular hollow waveguide, which forces the propagating wave to be either transverse electric or transverse magnetic, but not both at the same time. This is the major reason. Moreover, we will see TEM mode, transverse electromagnetic mode, neither the electric nor the magnetic field is present in the direction of propagation, say Z direction. A rectangular waveguide supports TE and TM mode but not TEM mode because it has only one conductor and cannot define a unique voltage. The side walls, we know it short circuits. It is a mode commonly used in coaxial and open wire feeders. So TEM mode is commonly used in coaxial and open wire feeders. Then there is a second reason. Maxwell's equations demand that there must be a component of electric and magnetic field in the direction of propagation, because if there is curl in the electric field and magnetic field along the axis of curl has to change with time, so cannot be 0 and it is no more TEM. So there is a video you can watch on YouTube, reference is given. On the right hand side we see the transverse electromagnetic mode with the direction of propagation along arrow mark. We can see the two fields, electric and magnetic fields, electric fields in the yellow shades and magnetic fields in the violet field marked. Now the field patterns, there are different field patterns. Field patterns for the dominant mode TE10, the electric field is maximum at the center of waveguide and drops off sinusoidally to 0 intensity at the walls. The very first diagram on the right hand side top view shows this, and the side view also you can see. The magnetic field is in the form of closed loops. It is forming dotted lines and forming closed loops parallel to the top or bottom of the guide. So it can be viewed from top or bottom of the guide, the loops of the magnetic fields. This applies to all TEM0, say 10, 20, 30 mode. In TE20 mode, there are two half-wave variations of electric field and magnetic field in the XY plane. The right hand side top corner, you can see the wave patterns, field patterns. TE11 mode, the third diagram pattern drawn on the left corner, is TE11 mode. The electric field looks like co-waves in the corners. Both electric and magnetic field have one half wave along XY axis and maximum electric intensity at exact center of waveguide. Then the right hand side bottom corner, see the TM11 mode. Electric field is radial and H field annular in the XY field. So there are questions asked to just to draw the field patterns. So these are the commonly asked patterns in the MSBT question papers. Now the circular waveguide. So circular waveguide will have the circular uniform cross section like a tubular circular conductor that supports TE mode and TM mode. The same laws that govern the rectangular waveguide governs here too, but with slight modifications. So what are the modifications or changes, differences? The cutoff frequency is given by the lambda 0, the wavelength, equal to 2 pi r by kr, where kr is solution of Bessel function equation. On the right hand side we can see the different mode and the corresponding kr value as per the solution, and r is the internal radius of waveguide. So TE11 is the dominant mode in the circular waveguide, as the value of kr, as from the table we can see marked TE11, the value of kr is 1.84, whereas in TM mode the lowest value we find is that of the mode TM01, 2.40. So for TM mode, TM0 is the in a way it is the lowest frequency that can be propagated through circular waveguide, and in TE mode 11 it provides the lowest frequency that can be propagated. So lambda 0 can be given as by substituting the value of kr into 2 pi r by kr becomes 2 pi r by 1.8412, the whole value it is 1.8412, equal to, that comes to 3.14 times r radius, that will become 1.7 times the d internal diameter of the circular waveguide, where d is the diameter. TM01 is the mode with the smallest kr value among TM modes, and m indicates number of full wave intensity variations around the circumference, and n is the number of half wave intensity changes radially out from center to wall. Now what are the field patterns generally asked? TE11 and TM11 mode, the two modes we can see and the respective field patterns. Then the advantage, what are the major advantages of the circular waveguide? It is easier to manufacture the circular waveguide compared to the rectangular waveguide, and even joining the circular waveguide sections is easier, and it is advantageous to use circular waveguide, when we have to transmit horizontally and vertically polarized both waves can be propagated in the circular waveguide. Disadvantage, drawbacks: larger cross-sectional area required to carry the same signal than rectangular waveguide. Means for a given microwave signal of the frequency, the circular waveguide will be of larger diameter than compared with the rectangular waveguide. The changes in polarization occurs due to the roughness and discontinuities in the walls that results into reflections rather than received at the other end. Applications of circular waveguide: it is used in rotating coupling or joints, in radars and microwave applications where both horizontally and vertically polarized signal propagation is advantageous or needed, and it is used in the hour mode, that is the higher order mode of the waveguide. Then next we see the comparison of rectangular waveguide and circular waveguide. So circular waveguide have a circular cross section that will be comparatively larger than that of the rectangular cross section in order to send the same microwave signal given microwave frequency. A rectangular cross section for the rectangular waveguide. Then TE11 is the dominant mode for the circular waveguide, and TE10 is the dominant mode for the rectangular waveguide. The lower cutoff frequency for circular waveguide is given by 1.8412 into C by 2 pi r, whereas for the rectangular waveguide the FC is calculated as C by twice A, where A is the width, longer dimension of the rectangular cross section, and in circular waveguide the attenuation is less, whereas in rectangular the signal is more attenuated, and it is easier to manufacture a circular waveguide compared with the rectangular waveguide. Applications: circular waveguides are used to connect a horn antenna with a reflector in the tracking radar, whereas rectangular waveguide is used in high power systems, satellite systems, precision test applications. Okay. So here are the references or learning resources one can go through to get more details, and the websites can be visited. So here at last we have the summary of what we learned in this presentation. We saw the rectangular waveguide, different modes: TE mode, TM mode, TEM mode. Then we also saw the different fill patterns, some of the fill patterns of TE10, TE20, TE11 mode and TM11 mode for the rectangular waveguide. Then we saw the circular waveguide, its advantage, disadvantages, the cutoff frequency for the circular waveguide, and the fill patterns of the circular waveguide, and at last we compared the two, rectangular and circular waveguide. So that's it. Thank you very much for watching.